In this video, we're going to look at limits of vector functions. So limits, the familiar concept of limits. So if you just recall quickly again that RT is a vector function and it is in fact has components ft, gt, and ht, then the limit as t goes to some number a, for instance, of r of t is effectively actually just in fact the limit as t goes to a of each one of these. So if you were to calculate the limit, it would be in this manner. And of course, the standard definition of the limits apply. I'm not going to look at the epsilon delta definitions that you might find in the textbook. All I would say though is that here what you're looking at is, if I were to look at a quick example, for instance, I would say a very simple one, for instance, r of t equals t squared and t cubed for the sake of argument. And if we were to calculate the limit as t goes to 2 of rt, then that would be in fact equal to the limit each one of these as t goes to 2, and that would be 2, 4, and 8, and that would be the limit of this particular function. So now that's basically all I'm going to say about limits of functions. Of course, the same concepts and same ideas apply about continuity. The tests for continuity about a point apply in the same manner as they would apply for standard functions. So derivatives of vector functions would be what we'd like to now quickly look at. So, of course, again, it continues from the fact that if RT is FT, GT, and HT, then clearly the derivative of this vector function dr dt, which can also be, and more likely we would be using this notation, r dash of t, is equal to, of course, f dash of t, g dash of t, and h dash of t. So in other words, again, please keep in mind that there are no new rules of differentiation that apply to each of these functions that you see here. In fact, these functions behave exactly the same way. The differentiation is done exactly the same way. Rules of differentiation do not change here. Okay, so for instance, a quick example of this would be if we go back to the previous example we looked at for the limits t squared and t cubed, then r dash of t is simply the derivative of t is 1, the derivative of t squared is 2t, and the derivative of t cubed is 3t squared, and so on. And in the same manner, we can continue to calculate derivatives. As long as we have continuous functions, we can continue to calculate the derivatives. Now, of course, physics, from a physics perspective, dr dt can be interpreted as the velocity vector v of t. So we'll just mention that for any of our science, physics, or engineering students, that it is simply this r dash dr dt is actually the velocity vector. And just for your reference, the velocity vector's magnitude is in fact the speed as we know it. So that's the speed, and this is the velocity. Okay, just quick references. And of course, that means that the acceleration vector A is in fact dv dt, okay, which is in fact d2r dt squared. So I just refer to these very quickly for anyone who might find those of interest. So in the next few properties that we're going to look at, we will be looking at, in fact, we will be considering u and v as vector functions, vector valued functions. These will be vector functions. C is a scalar, okay, and f, where you see it here, will be a scalar valued function. So this is in these properties that follow. So the first of these properties is if we were to differentiate the sum of two vectors u of t plus v of t, then that would simply be u prime plus v prime of t. Okay, there's not much that we can say about that. It's reasonably straightforward. And the same applies for if we were to take the difference of the two vectors and the derivative of the difference of two vectors. It will simply be the sum or difference of the derivatives of the individual vectors. The next one is if we were to take the derivative of a constant, a scalar times the vector. Again, it's quite straightforward. A constant doesn't change and has no effect. The linearity idea basically comes into effect here, and that's simply equal to u prime of t. Third property is if we look at in terms of products, what other type of products we have, then we would be looking at t multiplied by u of t. So here, in this case, the product rule applies as normal, and we end up with f dash t ut plus ft u dash t. So simple, straightforward product rule applies. Okay. Now, on the other hand, the next one we will look at here, if you like, I can give you a quick example of this one. Here, let's do a quick example of this. Here we would be talking about, for instance, if we had we're taking the derivative of, say, for instance, t squared into cos t, sine t, and t. Now the issue is when we are practically doing these. So when we're practically doing these problems, you will see that it's not that you have so many options. You could take the t squared inside, multiply it through the cosine, sine, and t, and then take the derivative. Or you could just follow the rule. So that would mean that you'd have 2t times cos t, sine t, t, plus t squared into minus sine t, cos t, and 1. Okay, and then you'd combine them and basically get the result. Okay, let's move on. Fourth property is if we take the derivative of the product of two vectors, vector functions. Now, product of two vector functions, there are two types of products of vectors and therefore vector functions as well. Same thing applies. And one of these is the dot product. So if we were to take the derivative of the dot product, it would again follow the same rule as the product rule, the familiar product rule, and you'd go, for instance, as follows. So you would differentiate u in the first instance and take the dot product with v, plus leave the first vector function u and take the derivative of the second one, v dash. So that's how that would work out. Now I'll do an example of this one also, but I have to be very clear on this, that the example of this, more likely than not, what you will eventually do is take the dot product first and then take the derivative of the result. Let me explain what I mean. Here, if I show you an example, so for instance here, if we were to take the derivative of the dot product of, say, t squared, t cubed, okay, dot product with cos t, sine t, and say t, then what we would end up with is the first thing we would do is we would take the dot product, and so we would have the derivative of, in fact, t cos t plus t squared sine t plus t to the 4. So we take the derivative of that, and of course that derivative is simply t cos t is a product, so you get cos t minus t sine t, okay, plus 2t sine t plus t squared cos t plus 4t cubed. So as you can see, more likely than not, you will first take the dot product and then take the derivative. Okay, but it is possible, of course, to follow the rule that's here. I'm not going to go use that because it's just longer and doesn't seem to be the right, in my opinion anyway, it doesn't seem to be the right way to proceed. So, or the best way to proceed. Right, it is certainly. Next property is the derivative of the cross product of two vectors. Okay, so we'll continue. So with the cross product, we end up with the derivative, again following the same rule, the product rule again of differentiation. So it's u dash t cross v plus u of t cross v dash of t. So that's what we end up with. Now you can clearly see here that what's going on is the product rule seems to be in all of these very clearly for the scalar valued function multiplying the vector, the dot product, and in the cross product case as well. Now again, I would advise you that when you are calculating the derivative of the cross product in this fifth property, it is more practical to calculate the cross product first and then take the derivative of the result, rather than calculating two cross products. As you've already seen, the cross product requires a bit of work to calculate. So doing it twice is quite a workload. So it is better to do the cross product first and then take the derivative of the resulting vector function. Okay, last one, the last rule we will look at is in fact the chain rule of differentiation here. And in this case, the chain rule, by the chain rule I mean when we are taking the derivative of u, the vector function, a function of tf essentially. And that is the standard derivative of f, of course, multiplied by the derivative of u and f of t. So it's simple as that. Now, practical applications of such properties sometimes are so obvious that you will never see this happen, in fact. So, I mean, it's very difficult for me to come up with an example of u of ft, for instance, okay, because in this case, say for instance, I would say u of t, for instance, is the function t squared and t cubed, and say that f of t here is, for the sake of argument, sine t. Okay, so it means that u of ft is in fact going to be sine t, sine squared t, and sine cubed t. Now the derivative of this would simply be, you would not really be using the chain rule as you see it there, but rather you would know, I mean, this, when you do this, the derivative of this, for instance, here would be u dash of t. The derivative of sine t is cosine t, clearly, straightforward. The derivative of sine squared t is 2 sine t cos t. Okay, and the derivative of sine cubed t is 3 sine squared t cos t. As simple as that. So that's what we end up with. Now, as I said, you are using the chain rule, but what you're doing really, if you think about it, is you're applying the chain rule to these three, this one, and this one, not really using this rule specifically. Not to say that you can't, but effectively when you're doing this, you don't necessarily follow exactly as the recipe that's shown here. Remember, these are formal rules of differentiation applying to various combinations of operations with vector functions. The final thing we will look at here is the interpretation of, in fact, r dash of t. Now, as you know, if we were looking at any function f of x and its derivative f dash of x, then we clearly know that f dash of x represents the slope of the tangent line. So here, if this is some f of x, then f dash of x at this point, for instance, is the slope of this line. F dash x represents the slope of the line anywhere. In fact, it's a formula for the tangent at any point. So in a similar way, r dash of t represents the tangent vector. So in fact, because I understand that we stay away from the concept of slope in 3 dimensions, we really concentrate more on vectors. So when we have in our 3D axes, as shown here, when we have some curve in 3 dimensions, which is a path traced out of some vector function r of t, then for instance, at this point, this vector that you see, this is the tangent vector at this point. But the formula r prime or r dash of t represents all the possible tangent vectors at all different points, or any different points on the path. So that's just a small thing I wanted to add, which is the interpretation of r dash of t. So the other idea I wanted to mention was the unit tangent vector. And the unit tangent vector is essentially the tangent vector r dash divided by its magnitude. So we normalize the vector, and that gives us the unit tangent vector by definition. We'll continue with these ideas a little later.